Good day, everybody. Today we'll be talking about the main group elements and the roles they play in life. Roughly 1/3 of the 90 naturally occurring elements play a role in human health and organisms in general. In this chapter, we will examine the various roles the different elements play in human health and physiological function. In this chapter, first we'll go over some main group elements and their relationship with human health. Then we'll follow this up with the periodic and the chemical properties of main group elements. Next, we'll go over the major essential elements and the trace and ultratrace essential elements. We'll also talk about non-essential elements and the elements for diagnosis and therapy. We can classify different elements based on their relative importance for good health and a normal body functioning. For example, the essential elements are those elements that are necessary for good health and a normal physiological function. These elements may be present in tissue and or blood, for example, hydrogen, nitrogen, carbon, oxygen, etc., or in bone like calcium, phosphorus, or in other bodily fluids. Non-essential elements are elements that have no known physiological function, but may have a stimulatory effect. In other words, they may enhance growth or promote some beneficial function. The essential elements can be subdivided based on the amounts that are present in the body. For example, major essential elements such as carbon, hydrogen, nitrogen, oxygen, calcium, phosphorus, potassium, and so on are present at levels greater than 1 milligram per gram body mass. Nearly all of these elements are readily available from the food supply. For example, calcium can come from broccoli and dairy products, and potassium, we can get that from bananas. Trace essential elements are present at the levels between 1 to 1,000 micrograms per gram of body mass and include some such elements like iron, iodine, fluorine, silicon, zinc, etc. The ultratrace essential elements are present at levels below 1 microgram per gram of body mass and include cobalt, copper, manganese, molybdenum, etc. The essential elements are summarized in this table as either major, trace, or ultratrace. The essential elements are almost always found in the form of compounds. Only oxygen is present in the elemental state as the dissolved oxygen in the bloodstream, although it's also found in compounds with other elements, for example in the form of water, carbon dioxide, bicarbonate, etc. Usually, when we refer to the elements in the body, we specifically mean their common ionic form. For example, when we talk about sodium, that means we are talking about sodium ion. Calcium, it would be calcium ion. Potassium, it would be potassium ion, okay, etc. So remember, most elements are found in the form of compounds. But oxygen, you can find it in the elemental form as O2, or you can find it in compounds like H2O or CO2, bicarbonate, etc., as we just mentioned. The non-essential elements are summarized in this table. Those that have a stimulatory role, including boron and titanium. Boron, titanium. Other non-essential elements or toxic elements may be found in the body due to the incorporation into the bone and or tissue. For example, lead-2 ion is toxic. That's lead-2 ion. Right. The reason is because lead-2 ion, Pb2+, may replace calcium in bone. And the rubidium ion is also toxic. For example, that's rubidium ion, because rubidium ion may substitute for potassium due to similarities in size and charge. So both of these ions, they are toxic. Because of their importance for maintaining good health, there are recommended levels for dietary consumption of the essential elements. The dietary reference intake, or DRI, levels are based on the recommendations of the Food and Nutrition Board of the National Academy of Sciences and are frequently revised to reflect the latest research. The recommended dietary allowance values have been replaced recently with the DRI, but you may still see food packages with RDA values. Notice similarities between the two sets of dietary recommendations. As we just noticed, some elements in the periodic table are harmful to human health. Inhaled radon gas poses serious health issues because it is an alpha emitter. It emits the alpha particles, which is dangerous to our health. Beryllium toxicity is most often encountered in industrial settings where the beryllium contaminated dust is inhaled. It can replace magnesium ions in the body, where it inhibits the magnesium catalyzed RNA and DNA synthesis in the cells. The lead toxicity is also well documented, as we just mentioned. It dates back to the Roman Empire, where it was used as a solder in plumbing. So that's why the Latin name for lead is so-called plumbum. The use of the gasoline additive tetraethyl lead was eventually phased out due to the concerns about the lead levels in soil near roadways. The use of lead-based pigments was also discontinued due to the concerns about the lead poisoning, especially in children. Lead acts as an enzyme inhibitor due to its ability to bond strongly with oxygen and sulfur groups. Now, let's quickly review some of the properties we have already learned in General Chemistry 1. The periodic trends for boiling point and the melting point are summarized in this table. The atomic radii and the main group elements increase as we descend from a group. So when you go from top to bottom, the atomic size actually increases. When you go from left to right in the same row, the size actually decreases. Okay. So for this reason, this corner will have the largest size. The top right corner, that will give you the smallest atomic size. The first ionization energies and the electronegativities decrease down the group and increase across the period. So you can see the right top corner, you will have the largest first ionization energy, and the left bottom corner will give you smallest first ionization energy. We have learned this when we talk about electronic configuration and the periodic trends. An overall trend toward more negative electron affinities is seen across a period. A survey of the main group elements reveals a variety of physical properties, as you can see in the table. For example, the melting points. In group 1, it will decrease as you go down the group. The boiling point will also decrease as you go down the group. Okay. For group 2A, it's very similar. The melting point will decrease down the group, and as well as the boiling points. For group 13 or group 3A, as you can see, there is no single trend that can be observed for either the melting point or boiling point. For group 14, or so-called group 4A, right, as you can see, there is no single trend for the boiling point, for the melting point. However, the boiling point does decrease as you go down the group. I want you to pay special attention for groups 17 and 18, or group 7A and 8A, because the trend for melting point and the boiling point, they are the opposite, as we have already learned when we talk about intermolecular forces, that both the melting points and boiling points for both group 7A, the halogens, and 8A, they actually increase when we go down the group. In this figure, we have noted the relative abundance of carbon, hydrogen, oxygen, and these three elements, carbon, hydrogen, and oxygen, they constitute 98% of the body. The top 11 major essential elements account for more than 99% of the body mass for a human being. The nonmetals are included in compounds such as amino acids, proteins, and the nucleic acids that represent the building blocks of the human body. They are also included in physiologically important polyatomic ions such as phosphates, carbonates, etc. Please note that the metals are present as ions, as we mentioned before. For example, potassium will exist as potassium ions. Okay. Calcium will exist as calcium ions, etc. The regulated concentrations for sodium and potassium ions are crucial to cell function. For example, too much sodium ion is associated with hypertension. To maintain the constant concentrations, cells need to be able to move the ions in and out of the cells. Because of the ions are not soluble in the lipid bilayer cell membrane, there must be mechanisms for ion transport across the cell membrane. The ion channel is a group of helical proteins that penetrates the cell membrane and allows for selective passage of ions based on size and charge. The so-called ion pump is a system of membrane proteins that are responsible for active transport of ions. This mechanism requires energy, which is provided by the hydrolysis of ATP to ADP. The ion pump is responsible for the proper nerve function. Stimulation of nerve cells causes sodium ion, Na+, to flow into the cells and potassium to flow out via the ion channels. This two-way flow of ions produces the nerve impulse. Recharging the system requires active pumping of sodium ion out of the cell, and potassium ion into the cell is a type of passive transport, because it could be done by something like so-called diffusion, which is natural. Okay. And by ion pump, it is so-called active transport. And it requires energy, usually provided by ATP being converted to ADP. The ion channel is illustrated in this figure. The helical protein penetrates the lipid bilayer. As you can see, these are lipids. This is a bilayer that's formed the cell membrane. And this protein, helical protein, okay, provide a path for ions of the right size and charge to diffuse between the inside and outside of the cell, as we just mentioned. This type of transport through ion channel is a passive transport by diffusion. Another mechanism for ion transport involves complexing metal ions with oxygen-rich molecules, such as non-actin, as illustrated in this figure. Because this complex between the metal and the non-actin has both polar and non-polar regions, it can pass through the cell membrane and transport the ion across the membrane. When ions are being transported from inside to outside or outside to inside, an electrical potential, E ion, will result from this concentration gradient of a particular ion on the opposite side of the cell membranes, as weighted average of the equilibrium potentials of the major ions based on the concentration and the permeability of the individual ions is called a membrane potential. The unequal concentrations of a sodium ion, Na+, and potassium ion, K+, on opposite sides of the cell membrane results in an electrical equilibrium potential. The equilibrium potential can be determined using the Nernst equation. We'll talk about that in chapter 18. We're not going to go over the details over here. So for now, you can simply skip this Nernst equations about the details. But do remember, the equilibrium potential or the cell potential is generated by the difference between the concentrations inside and outside the cell for the sodium ions or potassium ions. We are going to skip the details about the calculation for equilibrium potential or the cell potential. Now let's focus on the biological roles of the magnesium ion and calcium ion. The biological roles of the magnesium and calcium are more varied than those of the sodium ion and potassium ion. Calcium is a major component of bone and teeth. Prolonged deficiencies of calcium can lead to osteoporosis, whereas high concentrations in muscles can cause cramps. Excess levels in body fluids can result in the formation of calcium-based kidney stones. So too much calcium is not good either. Too little is not good either. Magnesium is a major component in the chlorophyll, one of the primary molecules in plants responsible for photosynthetic activity. Magnesium ions also play an important role in ATP hydrolysis and ADP phosphorylation. The role of magnesium in chlorophyll is illustrated in this figure, which shows the magnesium ion coordinated with 4 nitrogen atoms. The function of the magnesium ion is to orient the molecules in positions that allow the energy to be transferred to the reaction centers where water is consumed and oxygen is produced during photosynthesis. This happens in plants, not in human body. Chlorine is the only halogen present in sufficient quantities to be considered a major essential element. Chlorine is the most abundant anion in the human body and is involved in many functions. It's present in the body at 1.5 milligrams per grams of body mass. Like other major essential ions, chloride ions are transported into and out of cells primarily via the ion channels and ion pumps. Remember, ion channels gives you the passive transport, and if you use ion pumps, that's the active pathway. The malfunctioning of chloride ion channels are the underlying cause of cystic fibrosis. Chloride ions also play a major role in the elimination of carbon dioxide from the body. When the carbonate ion is pumped out of the cells during one step in the carbon dioxide elimination process, chloride flows into the cell to maintain the charge balance. Chloride ions are also present in high concentrations in gastric juices or the stomach acid, hydrochloric acid, which catalyze the digestive processes in the stomach. What about the nitrogen? Nitrogen is the major essential element found primarily in proteins, but also in DNA and RNA in the base pairs. Although abundant in the atmosphere as nitrogen N2 and in soil and water as nitrate ions NO3-. These forms of nitrogen are not available for use by the body. Excess nitrogen is converted into urea in the liver and excreted via the kidneys. Plants use urea as a source of ammonia, as indicated by the reaction on this slide. In this process, as ammonia reacts with water, it generates ammonia as the product. Nitrogen N2 must undergo redox reaction to convert it to a usable form. Nitrogen will be converted to, for example, ammonia, NH3, by nitrogenase enzymes in bacteria, and nitrates, which is NO3-, in soil, will be converted to ammonia by reductase enzymes in plants. Once in the food chain, the organic forms of nitrogen can supply the essential amino acids for human diets. There is no need for you to know the details how nitrogen is being converted into the useful form, or nitrates being converted to the useful form like ammonia. Phosphorus is found in DNA and the polyatomic anions prevalent in the environment. Biological phosphorus is the phosphate ion, PO4, 3-, and its conjugated acids like HPO4, 2-, which is called hydrogen phosphate, and H2PO4-, or dihydrogen phosphate, along with phosphate esters. Aqueous phosphate is transported into cells where it's essential to life, as shown on the slide. Phosphate is incorporated into molecules such as ATP, glucose 6-phosphate, and nucleic acid. Sulfur is found in protein and an array of sulfur compounds in the environment. Volatile sulfur oxides, SO2, sulfur dioxide, and SO3, sulfur trioxide, form and can dissolve in water to produce the weak acid H2SO3 or sulfurous acid, and the strong acid H2SO4, sulfuric acid. The sulfate ions produced in nature are all absorbed by plants. The enzyme ATP sulfurylase promotes the introduction of a sulfate into ATP. The trace and ultratrace essential elements are shown in this figure, with the DRI values in micrograms indicated as represented by the height of the column. One example for ultratrace essential element is selenium, that is found in the body at levels of 0.3 micrograms per gram of body mass, which is really small. Okay. And there is evidence that there is a minimum dietary required for the intake of selenium, although too much can lead to toxic effects. The dietary sources of selenium include garlic, mushrooms, asparagus, and fish. The only trace essential main group elements are fluorine, iodine, and the silicon. Fluoride ions have significant benefits for dental health and are often added to drinking water. The fluoride F- reacts with hydroxyapatite in tooth enamel to form fluorapatite, which is less susceptible to decay from acid by shifting the equilibrium to reduce the solubility of the tooth enamel. The body concentrates iodide ion, or I-, in the thyroid, where it is incorporated into two hormones that regulate the energy production and use. A lack of silicon can stunt growth in mammals. It is also considered beneficial in the form of silicic acid by reducing the toxicity of aluminum ion, Al3+, in organisms by precipitating aluminum as the aluminosilicate minerals. Rubidium is generally regarded as non-essential, but it is the 15th most abundant element in the human body. It is believed that rubidium is retained by the body because of the similarity of its size and chemistry to that of potassium ion K+. Cesium ion Cs+ are also readily absorbed by the body, but have no known function. They can substitute for potassium ion K+ and interfere with the potassium-dependent functions. In most cases, the environmental concentrations of cesium, Cs, are so low so that the exposure to cesium is not of concern. Recent nuclear accidents like Chernobyl have introduced a radioactive cesium-137 into the environment, where it can be incorporated into the plants and pose a significant health threat. Germanium is barely detectable in the human body. Antimony compounds are toxic and can lead to liver damage. However, ultratrace levels of antimony may have a stimulatory effect. Also, some antimony compounds have been used medically as anti-parasitic agents. Bromine has no known function in the human body, but it is consumed in foods such as grains, nuts, and fish in amounts ranging from 2 to 8 milligrams per day. Bromide has a sedative and anticonvulsive properties, but becomes toxic at concentrations around 100 milligrams per liter. Of the 30 also essential elements, some are also useful for diagnostic and/or therapeutic applications. In addition, there are many other elements, including radioactive isotopes, that are used in the diagnosis and/or the treatment of a wide range of illness. Any diagnostic or therapeutic compound that is injected intravenously must be sufficiently soluble in blood to be delivered to the target. It must also be stable enough to not undergo chemical reactions that may result in its elimination from the body. In some cases, the compound may be in the form of salt to increase the solubility, or it may involve the formation of a coordination complex, for example, in the case of metal cations. Ideally, the radioactive imaging agents should have short half-lives and the low energy gamma rays to limit the patient exposure to harmful radiation. In addition, the toxicity of the parent and daughter nuclei must also be considered, along with the cost and availability. Several isotopes of gallium and indium are used as imaging agents for tumors and leukemia. Do remember, not all imaging applications involve radionuclides. The lack of chemical reactivity of the noble gases and the ease of introduction into the body by inhalation makes them attractive agents. For example, these different forms of noble gas isotopes can enhance the MRI images. And the helium-3 has no known side effects and is obtained by beta decay of tritium. As we mentioned previously, lithium ion is similar to the size of the magnesium ion. Okay, the size is almost identical. So this allows it to compete with the magnesium ion in biological systems and may account for the toxicity of lithium ion at high concentrations. Despite of that, lithium compounds have been used to treat bipolar disorders. For example, lithium carbonate, that's lithium carbonate, that can be used to treat bipolar disorders. For group 3A, only boron and aluminum have been detected in humans. The role of boron is not fully understood, but it is believed to have been involved in the nucleic acid synthesis. Antimony compounds are generally considered to be toxic. As noted previously, for example, the use of antimony compound as fire retardant has resulted in increased exposure of infants to these compounds and has been linked to the sudden infant death, or SIDS. Some antimony compounds, however, have applications as anti-parasitic agents. Bismuth has been used as the over-the-counter treatments for indigestion and GI disorders. So, we have completed this chapter and we have talked about many applications of the main group elements. It's a lot of information. Please just focus on the most important applications of some of the elements. Know some of the concepts. For example, what is the essential elements? What is the non-essential elements? What's the trace elements? What is the ultratrace elements? So know some of the definitions, and that will be good enough for test-taking purpose. Thank you very much, and see you next time.